Welcome once again to our classes. Now we are discussing the metal-carbene complexes, and our obvious goal is to explore and to study its catalytic applications in olefin polymerations called ring opening metathesis polymeration, ROMP. So far what we have done, we have now discussed what are the metal carbenes and also metal carbynes, what are the basic structure, what are the metathesis, what are the alkene metathesis reaction, what are the type of alkene metathesis reactions, and we have discussed quite elaborately what are the possible the reactions can be done by the single metathesis catalyst. So we discussed in the last class that this can be termed as a single lock for single key for multiple locks. Okay. So now today we will focus our discussion on the metal center. Okay, and what are the electronic properties and what are the bonding interactions between the metal and the organic carbon forming the stable metal carbene complexes. Okay. So today's topic is bonding and electronic properties in metal carbene complexes. Okay, this is very much important to understand in depth, because if we want to design a metathesis catalyst for polymerization reactions or any other reactions, we have to be really very clear concept about the metal centers, about the ancillary ligands, and about the carbene fragment. Okay. So the concepts we learn here: the bonding in metal carbene, electronic properties, and the different type of metal carbene complexes mainly classified into Fischer and Stock. So what are the Fischer carbene and what are the Stock carbene, and why, what is the basic difference between the Fischer and Stock carbene in the bonding as well as in the electronic properties. As you know that electronic properties actually dictate the reaction, okay, the reactivity. So it is very much important to understand the difference between difference in electronic properties in the Fischer and Stock carbene. So that is our target today. Okay. So this one, these are the two types of the metal carbene complexes. So in the last class, in the beginning, the first class of the metal carbene, we discussed that these are the metal carbene complexes. You can regard is like this one. Okay. So here is, let's say, this is the just arbitrary, I mean not real molecules. So in obvious, in formally there is a metal carbon bond. Okay, the two is a double bonds, metal carbon double bonds. Okay, two bonds. Okay, and if you think about the canonical form, you can consider as like M plus, okay, C minus, okay, and the other one is M minus C plus. Okay, so we will really try to understand today that whether this is a possibility or not, whether this two canonical structure, okay, or whether the difference in the electronic properties of the metal centers and the carbon of the carbene centers are really possible or not. That we will try to understand today. So if it is, let's say, the left hand side, okay, that the metal is nucleophilic, that means it is electron rich. Okay. So if it is like that, so if it is nucleophilic, then, and obviously the other one, the carbon of the carbon center will be electrophilic. Okay, that means here the nucleophile can react here and electrophile. Okay, so it will undergo the nucleophilic reactor attack on the carbon and the electrophilic attack on the metal center. Okay, and if this scenario exists, then this is the Fischer carbene complex. Okay, so here in the Fischer-carbene complex you will see that metal center is nucleophilic in nature. That means uh, uh, and the carbon center is electrophilic in nature. Okay, that means this is the this one M minus C plus. Okay, now the other scenario, that is the opposite. Okay, where that your metal center is electrophilic in nature and the carbon of the carbene is nucleophilic in nature. That means this is the electrophilic attack can happen on the carbon and the nucleophilic attack can happen on the metal center. So exactly difference it is. Okay, and here, so in this case you will see that this is the best representative of this canonical structure, that is the this one. Okay, so yes, it is possible depending on the proper designing of your carbene, organic carbene, and also the choice of the metal center. As example, like for here the Fischer-carbene. Okay, here you will see that this is the low valent, generally 0, +1, +2 or -1. Most maximum is generally +2. Okay, and here you will see this is generally middle or late transition metals from this kind of Fischer-carbene complex. And another criteria of this kind of Fischer-carbene complexes, that here you will see that there is the pi donors, as example oxides or amides or any other like sulfur should be attached, okay, with the carbene carbon. As example, like here CO5, okay, tungsten, and here OMe, and here it is the methyl. Okay, so here that's why you see this is the heteroatom, that the X, okay, and with that one any other alkyl groups may be there. Okay, and we'll discuss why it is like that. And this is the soft carbene. Here the difference is that the metal center is high valent, okay, late transition metals generally. Okay, and here you will see that this the R groups, that is the on the carbene carbon there are alkyl or hydride or CP groups on the metals as ancillary ligands. CP groups on the metal center. Okay, okay. As example, okay, that tantalum CP, okay, and this is CH2, and here is CH3. Okay, this is one example. So here either the hydride you see or any other alkyl groups, okay, and on the carbon of the carbene there should be the alkyl groups, okay, and also the CP groups on the, in general, CP groups on the metal centers as ancillary ligands. Okay, as example here you see this one. Okay, now for the Fischer-carbene, as it is low valent, so generally the good pi acceptor ligands, as example carbonyls, okay, the phosphines are generally on the metal as the ancillary ligands. Okay, so these are as ancillary ligands because these are the low valence. So to stabilize the low valency of the metal centers, we need to have a good pi acceptor ligands. Okay, and here that I discuss after some time that why the importance of this O group, O or amide. Okay, this acts as a pi donor of the on the Fischer-carbene. Okay, so these are the basic structure of the Fischer and Strock. Okay, so basic structure of the Fischer-carbene and the stock carbene. You understand, okay, how what the basic difference. Okay, obviously from as a simple, it looks like as a simple model, it looks like in both the cases are the metal carbon double bond, but the electronic properties are just reverse and very much different, and one here is M delta plus and other cases is M delta minus. Okay, fine. So this is before going in more depth. Okay, so we this is a good information and important informations. We if you see the recent papers or the books or the reviews, we generally become very excited if we can replacement of the phosphine ligands, okay, in any catalytic system. Okay, why you are interested? Because the phosphines are generally toxic, environmentally is not good. Okay, hazard is regarded as environmentally hazard compounds, bad smells obviously. Okay, and it is not bio-friendly. Okay, so that's why if we can develop a catalyst by replacing the existing catalyst, okay, by exchanging the phosphine with any other ligands which are eco-friendly, I mean environmentally friendly and not toxic, as example like N-heterocyclic carbene or carbene, we become really very happy and it's more acceptable. And why? Because without sacrificing the electronic properties, because the electronic properties of N-heterocyclic carbene and the phosphines are very much similar. Okay, and basically the stabilizing and too much compromising of its catalytic activity. Okay, why it is like N-heterocyclic carbenes are also a good sigma donors. Okay, as example as compared to the phosphines, and these are actually better sigma donors than the phosphine ligands. Okay, so is actually better sigma donors than the phosphine ligands. Reactivity wise, NHC hydrolyzes rapidly, but the aryl phosphines are not that much sensitive in water. Okay, however, however, in presence of oxygen, okay, in presence of oxygen, it undergoes the oxidation reactions. Okay, the phosphines. So, like what it is formed? It is formed like in aerial, undergoes the aerial oxidation and form like the P double bond O. Okay, POR3. Okay, and you see it undergoes from the oxidation from +3 oxidations to +3 to +5. So its electronic property is completely changed. Okay, so it reacts, the phosphine reacts rapidly with oxygen. Okay, but NHC does not react rapidly with oxygen. Okay, so actually there is a mistake here. It will be O2 and here it will be H2O. Okay, fine. And another is that if you consider about the steric bulkiness, the requirement of the NHC, later I will discuss that the N-heterocyclic carbenes generally, okay, are stabilized if there is a sterically hindered groups. Okay, so for if you consider the steric hindrance, the NHC are more sterically hindered, sterically demanding compared to the phosphines, because in phosphines you can change, if you recall the Tolman angle, cone angle. Okay, Tolman cone angle is basically the quantifies the steric bulkiness of the phosphine. You can tune very nicely. Okay, if you need a less steric demanding phosphines, you can take a smaller R groups, and if you need a bulkier, you can choose accordingly. Okay, and in heterocyclic for in heterocyclic units you have a stronger metal carbon bonds. This is much stronger than the metal phosphine. Okay, bonds. Okay, and that's why in sometimes it is difficult, okay, to replace the carbene carbene bond by the phosphines. However, the vice versa is very easy. Okay, so the so in the carbene complex, metal carbene bond is much stronger than the metal phosphine complexes. Okay, fine. So these are information, because in catalytic chemistry you will see in many cases that it is claimed that yes, this catalyst is designed by replacing the phosphines by the carbene. So it is good to know that what the advantage and disadvantage. Okay. Now let's come to again the more detailed discussion about the fissure carbene. Okay, and we will discuss in very qualitatively by the with the help of the orbital interactions or Diochart model. Okay, so in the beginning of our class we discussed that this is a singlet carbene, and you see that this is the sp2 hybridized. Okay, and this is my pz. Fine. So now we have this one is a one lone pair. Okay, it is housed in the sp2 orbital, and this is singlet carbene. And now if we have the metal d orbital, suitable metal d orbitals, so here you will see that this is, if any kind of a d sigma, you know that d sigma we can the 5 d orbitals we can categorize as d sigma and d pi. D sigma is dx square minus y square and dz square, and d pi is dxz dyz. Okay, and dxy. Okay, so this is, you see that any of the d sigma orbitals which can interact as a sigma bond fashion. Okay, so what will happen, this lone pair will be donated to the empty d orbitals. Okay, empty d orbitals, d sigma orbitals of the metal centers, like here. Fine. Okay, here. Now okay, and you have now you have a pz orbitals, that is the empty pz orbitals. Okay, and you have a d pi orbitals, filled d pi orbitals. If you have, then there is a possibility of back bonding like this one. Okay, so as you in the last slides we discussed that generally, okay, in the fissure carbene complexes you have this kind of moiety M C. Okay, and you have the O R, and you have any other R group here. Okay, and you have this one, you have this one. Okay, you have a, so this is basically as a pi donor. Okay, and this is empty pz orbitals of the carbon, and this is the d pi orbitals. Okay, like this one. Okay, now you have to consider that this is a poor pi acceptor. This is a poor pi acceptor. Okay, and that's why what happens, that to stabilize this back bonding is quite less. Okay, so the pi donors substituents like OR and NR2, okay, here, okay, on carbene carbon is essential. Okay, and there is reduced back donation from metal d orbital, d pi orbital to pz of carbon orbitals. Okay. So now what happens, this one there is a like this kind of extended conjugation is like that. Okay. So if you can imagine like this one, okay, R O R, okay. So here the lone pair is there, so it's like that. Then so OR plus and here the R. Okay. So M will be more with delta minus. Okay. So here what happens, this carbon is electrophilic delta plus on carbon. Okay. So that's why you will see that there is one sigma bond between the carbon to metal, that is the donation from the sp2 orbitals, electrons housed in sp2 orbitals of the carbon to the d sigma orbitals, empty d sigma orbitals of the metal, and the back bonding is quite poor, and as a result you will get the delta plus on the carbon center. So here it is, in this case what happens in the Fischer-carbene complexes, here you will get a delta plus and you will get a delta minus. Okay. So this is the bonding interaction between the between the metal d orbitals and the carbon orbitals in the Fischer-carbene complexes. I already discussed that the role of the other substituents and also the ancillary ligands, because here you will see that low oxidation state metals are generally form the Fischer-carbene complexes. Now what will happen in the Stock-carbene? So in the Stock-carbene, the carbenes are actually triplet carbene. Okay. And what is happening here, the bonding interaction is quite different, and that is also reflected in its electronic properties. So what is happening here, you will see that in this case, as we already discussed, that this is a generally higher oxidation state metal, transition metals. Okay. And in this case R groups are generally H, okay, or any other alkyl groups, and here the Cp as ancillary ligands. Okay. Ancillary ligands. Okay. Now here what is happening here, you will see that this is the sp2 orbitals of one electron and one electron in the pz orbitals. Okay. So now similarly, that if you this electron is donated to the d sigma orbitals, okay, of the metals, and form like a real covalent bond. Okay, because you have also one electrons in the d sigma orbitals. Okay. Now in the pz you see the d pi orbitals, if there is a one electron, two unpaired electrons on the metal center, one is on the d sigma and one is in the d pi, then this is the best fit for the Stock-carbene complexes if you have the triplet carbene. So this is pz and pz. So here you will see that there is a bond between the metal and carbon to formal covalent bond. Okay. So here the scenario you will see that this is the one sigma bond and one pi bond, because one is forming like a sigma fashion, d sigma and sp2, and one is the d pi and the pz orbitals. Okay. Now here you will see that one of the real example I already discussed, that this is like this one. Okay. So if you have the CH2 and this is basically the methyl, the tantalum, you will see that oxidation state is tantalum is here +3, and In this case, as the metal carbon is more electronegative, and metal is electropositive. Okay, so that means this is delta minus and this is delta plus. So here you will see the nucleophilic, okay, delta minus on, so carbon is nucleophilic and as delta minus on the carbon. Okay, so that is the basic difference in the electronic properties between the Fischer and Stock. Okay, and accordingly the reactivity difference are observed for the Fischer and Stock carbene complexes. Okay, fine. So in here you will see that for Fischer carbene, the qualitative orbital interactions, from the qualitative orbital interactions, so what are realized and or postulates we can do for the Fischer carbene, and I am writing here Stock carbene. Okay, so here you will see that the carbenes are sigma donor, because this is singlet and singlet carbene, because these lone pairs are on the sp2 orbitals. Okay, and the p orbitals is weak acceptor. This is very important to understand. Okay, so that means the m d pi to pz of carbon is not very this is interaction is very weak interaction. Okay, so that's why you will see that nucleophilic and that is the reason why you get that this is the C is with delta plus and metal is with delta minus. So this is now very much understandable. Okay, and here the Fischer carbene, it acts as a like a L ligand L. So it's the carbene here is like L, so neutral ligand. Okay, just a neutral ligand. Now in the Stock carbene you will see that is basically the M double bond C is like a covalent, two covalent bonds. Okay, in the Stock carbenes. Fine, and here so two electrons of triplet carbene interacts with two unpaired electron of on metal d orbitals. Okay, one is d sigma and one is in the d pi. Fine, and as you see that there is a carbon is more electronegative, so this is C minus and this is plus, so entirely different. And here as it is formed two covalent bonds, so this actually acts as a X2 ligand. Okay, so behave as a X2 ligand. Okay, that the triplet carbene in the Stock complexes, Stock carbene complexes, and here it is as a L ligand. Okay, so you will see that totally different in the bonding as well as in the electronic structure. Okay, so if you see the very simplified molecular orbital diagram of the Fischer carbene complexes, so here the metal d orbitals, that is you will consider as a d pi here. Okay, and this HOMO, you will see that this one is a more metal like character than the ligand, because you will see here that this is like a more close to the metal d orbitals, and the LUMO here, this is close to the LUMO of the free singlet carbene, and that's why the LUMO is more ligand character than the metal character. Okay. So here this is the LUMO and this is the HOMO. So in a HOMO, the character of the HOMO is more like a metal like, so that means the it is has more contribution from the metal d orbitals, and LUMO will be like more like a ligand character. Okay. So this is for the Fischer type of carbene, and entirely different in the your stock carbene. Here you see that HOMO will be in the HOMO, it will be like a more ligand character, like you will see that this is the more very close in energy to the triplet free carbene orbitals, the HOMO of the triplet free carbene orbitals, and the LUMO, that is the this one. Okay, you will see that is a more like a metal like, because you will see that this is very close to the metal d orbitals. Okay. So the that's why the reactivity is much more different in the Fischer and stock carbene. Okay, you see the LUMO, in one case LUMO is more metal like character like in the stock carbene, and in the earlier case you will see that it is more like ligand type character, that is for the Fischer carbene complexes. Okay. So from our discussion about the orbital interaction, the electronic properties, now it is very much clear that what are the electronic properties on the carbon centers and the metal centers, and what are the basic properties of the metal carbon bond. Okay. Now this is the Fischer carbene complexes. So we already discussed that carbon is electron deficient. That means it is act as a C delta plus, D delta minus, and why it is deficient we have already discussed. It is stabilized by heteroatom, that is the oxide, amide, like that. Okay, and is attacked by the nucleophiles. Okay, so here this is, it will attack very easily here, and here the electrophiles, like that. And metals, okay, it's here it will act as a electrophile, and it is as it is a low oxidation state, so it generally stabilized by electron accepted ligands, as example carbon monoxide or phosphines. Okay, and in the Fischer carbene, okay, you will see that it is basically a in between single and double bond, because you will see this sigma donation is strong. Okay, and but the back bonding, that is this one, is weak. So that means you will compared to the stock carbene, where you will see that you have a two covalent almost covalent bonds. So here the reactivity the metal carbon bond in stock carbene is quite strong than the Fischer carbene. Okay. So and as a consequence, you will see that the low rotation barrier is observed for metal carbon. Okay, but in the case of stock carbene, it is the large rotational barrier. That means, okay, so if you have like this one, R1 and R2, okay, it can exchange, okay, because the metal carbon bond is very low. Okay, but for stock carbene it is not possible. Okay, so here the exactly reverse of the stock carbene. So this is electron rich, that means this is delta minus and delta plus. Okay, and here you see that we already discussed about the why the difference it is. Okay, in one case delta minus and one case delta plus on the carbon. Okay, and exactly reverse on the metal centers. Fine. Okay, so these are the other classes of carbene complexes, where you will see, we will discuss later, that is these are vinylidene complexes. This is another carbene complexes, and this is again the carbon center is electrophilic, and here R1 and R2 are more like alkyl aryl, so highly sigma donor type of ligands. Okay, those are all sigma donors ligands. Okay, So here also alkyl and aryls here, okay. And here you will see this is a very special type of carbene. This we call NHC, N heterocyclic carbene. We will discuss in the later classes. This is a very special category of carbene ligands, okay. So here you will see that this carbene, this is the carbene carbon, okay. This is, and this kind of design is very much important to stabilize the carbene. Why it is so, we'll discuss later, okay. You just now try to understand what is the versatility in the metal carbene complexes, okay. So similarly, okay, about the metal carbene, we have also the metal carbine complexes, fine. So this is the metal carbine complexes. So if you understand the metal carbene complexes, the orbital interaction, you will be able to draw the qualitative orbital interaction for metal carbine also, okay. What are they? Let's draw with me, then you will understand. So this is the metal carbine fragment. So let's say this one. So this is, okay, so you understand this is the sp hybridized carbon center, okay. So you have this one, okay, and you have, okay, now, and okay, so this is the 2p orbitals, okay. One is, so I can, let's say, plus, okay, and plus, minus, minus, and you have another electron that is, let's say, here, okay. Now consider the metal orbitals, okay, like here, okay. So this can donate to the d sigma of the metal, okay. So this is basically the sigma bond formation, okay, and this one again is a pi bond formation, okay, and this is back bonding possible, because you will see that this is my empty pz, okay. So there is a, from the field d orbitals, d pi orbitals to the empty pz orbitals, so back bonding possible, okay. So this is the called the Fischer metal carbine complexes, okay. So if you consider that up to this one, okay, and this one, so it is a basically L type of ligand, okay, the neutral ligand, like just like a Fischer carbene. And if you consider the pi bond, so this is basically Lx. So that's why here, okay, the carbene where it is regarded as a Lx type ligand in Fischer metal carbine complexes. Now you consider the Stock type of carbine ligands, carbine complexes, okay. What are the basic difference? Again, you draw the carbine. So here, so plus, minus, plus, minus. Now what are the electronic arrangement? So 3 electrons total I have to arrange. So this is 1 electron here, 1 electron here, and 1 electron here, fine. Now if I have a metal center, okay, now what are the possibilities? Okay, the possibilities that this, if there is a 3 unpaired electrons, then it can form 1 sigma bond here through the d sigma of the metal centers. Now here another pi bond, okay, fine, and the another pi bond here. So you see that 3 bonds are possible, okay. So here metal carbon, here you see that 3 covalent type bonds. Okay, and here you will see that 1 covalent and other 2. Here this is the covalent sigma donation, 1 pi donation, 1 back bonding. Okay, and that's why this is regarded as X3 ligand. So I hope you have understood the difference between the X3 and XLX. So here I will see that 1 covalent bond, okay, and this is actually, this we should not write, this is 1 covalent, this is the 1 covalent real, this is we should not tell, this is we can simply tell the sigma donation, okay, to avoid the confusion. Okay, so here you will see 1 covalent, that's why this LX is there. So here it is LX type and here it is X3 type, okay, in the stock carbonyl complexes. Okay, so obviously the bond strength is much higher for the metal carbine in the stock type of complexes compared to the Fischer, which is very similar to the metal-carbene complexes also. So bonding interaction is very much similar as metal-carbene complexes, so I will not discuss in more depth. However, if you understood the concept of the metal-carbene, you can apply to the metal-carbine complexes also. Okay, so in conclusion, okay, we have we can list out that what we are the conclusion from the today's lectures. The first one is that the 2 main categories of the carbene complexes, one is the Fischer and one is the stock. Okay, and the Fischer carbene complexes, you will see that this is carbon is electropositive and here it is electronegative. Sorry, the carbon is delta plus and in the metal it is delta minus, and in the stock exactly it is opposite. Okay, so here it is delta minus and it is delta plus. Okay, and that's why the carbon center is electrophilic and here it is nucleophilic in nature. Okay, so you understand that how different it is, and also we have understood the qualitative molecular orbital diagram of the Fischer and the stock, and you see that LUMO character of the LUMO and HOMO are entirely different, as actually the just reverse in the stock carbene complex to the compared to the Fischer complexes. So in this class we have understood that what is the basic difference between in the bonding and the orbital interaction in the Fischer and stock type of carbene complexes, and we have understood that why the carbon center is totally different in view of the electronic properties, okay, in for the Fischer and stock type of complexes. Okay, so these are the references you can consult all very popular textbooks, and in the next class we will be discussing about the basic synthetic protocols of the metal carbene, both Fischer and the stock type of carbene complexes, also the metal alkylide type of complexes, and then we will discuss about the reactivities. Okay, we will also try to introduce the one of the very popular carbene complexes, that is the metal N heterocyclic carbene complexes, as you see the basic structure of the Graf's catalyst, okay, generation graph, you will see that one of the phosphines has been substituted by the N heterocyclic carbene complexes. Okay, so it is important to understand about the N heterocyclic carbene complexes. This is becoming very popular in various domains. Okay, so thank you very much, and then we'll again see you in the next class with the continuing our discussion on the Metal-carbene. Thank you, and till then, bye bye.